We are Team Marima Notes, and this is our final project presentation for time series analysis. Our project focuses on forecasting clothing retail turnover in Australia using time series methods, particularly Sarima modeling. We use monthly retail turnover data for clothing, footwear, and personalized accessories in Australia from April 1982 to March 2025. The data is seasonally adjusted and sourced from Australian Bureau of Statistics. From the time series plot, we can see that there is a strong upward trend over the 40-year span, reflecting economic growth and inflation. The plot shows clear annual seasonality with sharp peaks that likely align with the end of the year holiday shopping. We can see variance shifts around the 2020, since the COVID period, which introduced greater volatility and irregular consumer behavior. There is a structural change around 2020, possibly due to the permanent shift in consumer spending habits or the rise of online retail. You can see persistent long term growth, which is crucial for building forecasting models. Next, we use ACF and PACF plot to diagnose the properties of the series. In the ACF plot, we see a slow decay and strong spikes at lag 12 and 14, which indicates that the series is non stationary and requires differencing. There's a clear annual seasonality, which is a strong signal for seasonal modeling. In the PACF plot, there's a sharp cutoff after lag 1 with no strong spikes beyond that. This pattern suggests an autoaggressive component of order 1 or AR1, which is likely useful in our Sarima specification. To determine a suitable Sarima model, first we applied both seasonal and non-seasonal differencing, as shown in the top left plot. The resulting series appears stationary with fluctuation centered around 0, although variances increase noticeably after 2020. The ACF plot on the top right confirms strong annual seasonality with significant spikes at lag 12 and its multiples, while the PACF plot shows a sharp drop after lag 1, supporting the inclusions of non-seasonal AR1 component. The BIC heat map in the bottom left highlights components of AR and MA term that minimize information criteria with the darkest regions indicating promising candidate structures, especially around AR2 and MA2. Adjacent to that, the AR-MA grid summarizes all tested combinations where circles represent viable models and crosses indicate convergent failures or poor performance. Based on these diagnostics, we shortlisted 6 Sarima models. We will further test these models with various parameters. We evaluated the models using AIC, BIC, MAE, and RMSE. The model Sarima 311-111-12 achieved the lowest JIC and RMSE values, indicating strong in-sample performance. However, it contained at least one statistically insignificant coefficient, which raises concerns about overfitting. On the other hand, Sarima 212-111-12 has comparable performance while all its coefficients were statistically significant. Therefore, we selected Sarima 212-111-12 as the final model, balancing accuracy and reliability. Residual analysis is essential to validate model accuracy. In our case, the Shapiro-Wilk test showed a p-value of less than 0.05, indicating residuals are not normally distributed. The Young test also returned a p-value of less than 0.05, suggesting that autocorrelation remains in the residuals. The ACF and PACF plots of the residuals show significant lags, implying that some structure in the data remains unmodeled. So while the model performs reasonably well in terms of forecast accuracy, these residual diagnostics indicate it may not fully capture all underlying dynamics. We may need more complex models like Gart's model to fully capture the volatility present in the time series. We have used the Sarima 212-111-12 to forecast the clothing retail turnover for the next 10 months, and the forecast bar shows an upward trend with growing uncertainty intervals, particularly in the 95% confidence bands. In conclusion, we have analyzed over 40 years of monthly clothing retail turnover data in Australia. We have observed clear trends, strong seasonality, and COVID related variance shifts. Using ACF, PACF, and error metrics, we have identified Sarima 212-111-12 as the most robust model. However, residual diagnostics suggest room for improvement. Thank you.